Hello, everyone. So today we are going to continue our generative AI class, and we are going to dive into the world of autoencoders. So before that, I would just to go through the outline. And so today we are going to start our class with some examples, like as a motivation. We're going to discuss few use cases like of autoencoders, where autoencoders are really useful, okay? And then we are going to learn more about the definition and what exactly are autoencoders. After that, we are going to go through multiple architecture, starting with a very simple one, which is like kind of simple autoencoders, which is based on a single fully connected layer. And so I am going to show you like kind of a demo each time we are going to go through the notebook I have prepared for you guys. So we will see and explore together the coding side as well today. So we didn't do this yet in this class. So today we are going to explore coding. And we are going also to discover a sparse. What is a sparse autoencoder? We are going to implement that as well. Probably it's going to be your task. And we will see what is deep, fully connected autoencoder, convolutional autoencoders, and we will see some example like where we are going to use this powerful tool for image denoising. And probably we will discuss about sequence-to-sequence autoencoders. And so it's kind of perspective, or I am opening the door for you here to explore new things, okay? So let's start with the example. So this was the example of last time. So this is an AI-generated image. I was giving the picture of a baby who is only 3 years old, and I was asking AI to like predict or generate an image of this baby once he's going to be 8 years old. Okay, so this is going to be our example. Now, AI, as I mentioned last time, could be used, generative AI, I mean, and in particular, autoencoders could be used for image reconstruction. Okay, so here what we have is this image, as I shown you last time, is kind of damaged, it's kind of noisy, it's like part of it even are missing. So this doesn't look quite perfect. So how mainly we obtain kind of a new, I would say, clean, nice, reconstructed version of this image is mainly thanks to the autoencoded architecture, okay? And so mainly I would maybe later I will come back in details like about to how this architecture works mainly, but quickly we know that autoencoders, they take the image as an input, and this image is like going to go through what we call the encoder part, okay? So the encoder part here is going like to compress, I would say, the noisy old image into what we seen probably last time. We were talking about latent variables. So in this case, we are going to talk about what we call latent representation of this image. So we are kind of going to compress it, and from an image with, I would say, dimensions, probably I would say 300 by maybe 200 pixel, which is having many pixels, we are going probably to end up having just an illustration here for points. So we are going to summarize things. So from a big representation, the idea is that we are going to have a compact latent representation. Okay, so we denote this with Z. And so mainly this is going to maintain the important, I would say, or it's going to store the essential visual features, okay? After that, so this is going to go through the decoder part, where we are going to reconstruct from like this latent like representation of the input. So we will reconstruct the image. Okay, there is kind of a similarity, by the way, between these two images for sure. And this is what I will explain later when I will be discussing the details of this architecture. But mainly, we are discussing use cases. So keep in mind that probably the first use case or application of autoencoders that they are using for image reconstruction, okay? Also, they could be used for image colorization, which means like here, the autoencoder learns to map. Here, what we have is the grayscale like input. The autoencoders here is mapping that into kind of a colored or version of the image. So this is the colored reconstruction, I would say, of the image. And this mainly captures the color features during training, okay? All this will come back in details, but what I want you to learn that if you have an autoencoder, you are giving kind of a grayscale image, it could like reconstruct or give you the corresponding colored image. So this is another application of autoencoders. And here the most interesting one, in my opinion, is how to generate higher resolution images, which means, as you can see here, if you compare the resolution of this input image with the resolution of this output image, like after going through the encoder, decoder architecture or the autoencoder, so you see that this one is the low resolution. And now going through the encoder, it like kind of compress it again, try to reconstruct things. We are having the latent space Z here, storing again the important features. The architecture is the same. Then what we do here during the decoder is like we are learning kind of missing details. The network in this case or in this kind of block is predicting the high frequency information, is predicting ages, for example, texture, color in this case. So in order to enhance the quality, and as a result, what we have here is the high resolution output image. Okay, so just kind of a note I want to let you know here. So in this case, so what we call is it's kind of supervised learning, because what we have is the input low dimensional or low resolution, sorry, image, and the output is the high dimensional resolution or the new version of the image giving high dimension, okay? So here probably you might get surprised to see the word supervised training. So you would say probably, what is she saying? Like, because most of people like are familiar with standard autoencoders. So we know that standard autoencoders are typically unsupervised. So in that common setup, the network just simply learn to reconstruct the input, like previous cases we see. Like, for example, if we are taking the noisy image, we will see later an example, and we are going to produce the clean version, okay? So we will do this like later, like in terms of code. For this is unsupervised learning. The input and the output are the same, and the network kind of just compressing and then like decompressing the information. However, in this case, which is generating higher resolution image, we are using a particular like kind of autoencoders, which are convolutional autoencoders. And so the use in this case, it's for super resolution. So in this case, how it works, so it works differently. And here the input is low resolution image we have, and then the corresponding output is the higher resolution image. So the network in this case must learn to generate details which are or that are missing in the low resolution input, like texture, like ages, and so on. So because the network here trains like on pairs of low resolution, high resolution images, so this is a supervised learning task, okay? So even though we are still using the convolutional autoencoders architecture, so in this case, it could be seen as supervised training, okay? So the encoder compresses the important features into the latent space, and the decoder reconstructs like a higher resolution output, okay? So the key takeaway mainly is that while standard autoencoders, they are unsupervised and reconstruct the input, let's say, super resolution autoencoders are supervised and they actually enhance the input. They're producing kind of sharper or more detailed images like you can see in this case, okay? So mainly, this is all for the first three use case. Next, now we have the fourth one. The fourth one is another interesting application or use case where we have the application of or the use of autoencoders, encoder-decoder architecture, in the particular case of image search. So here probably you can ask yourself how mainly for example, I have Google and I have an image. I want to make sure that probably this exists somewhere in the web or doesn't exist. So I am going to search using the query or the input to the search engine is going to be an image. So here we are going to feed or to give as input an image. How it works? Have you ever thought about that? So mainly it's based on encoder-decoder architecture. It like takes the input. It's going to move on, I would say, from the big or high dimensions that we have here towards that vector C. We're going to compress or encode the information into some kind of, have a latent representation of the input. And then we are going kind of just decompress that or go through decoder to reconstruct. So what we have here, it's kind of sometimes fuzzy version. It depends on the parameters, and we will see all this in details later. So this is how we can have, this is our input or query. And here they are the different results. They could be similar somehow. There could be some little differences. There could be huge differences, but mainly this is how it works for image search, okay? So this is another interesting use case. And also we have the case of data compression. Data compression is mainly a different concept where when we have kind of, for example, you have the image, you have your USB, I'm just giving an example, and sometimes you think that your phone or whatever, you do not have enough space and you care about the space because images that are in, I would say like this one, higher resolution, usually they use more, I would say, space for storage or whatever. So if I want sometimes to decrease, I would say, the storage, or I want to save some space, at the same time, I want probably to have the same image. So what we do is usually to compress the information. And the idea of compressing the information is to keep the overall structure, but the quality of the information, we make sure that we do not lose for sure that much quality, but somehow there is a kind of reduction in terms of quality, okay? So this is mainly just quickly how data compression or image compression in particular works. And so mainly now we've seen different use cases. If I may probably think that the first three ones, that image reconstruction, image colorization, and generating high resolution images, they probably use a particular type of autoencoders. We are going to cover different types later. We will see the simple one, the simple fully connected autoencoder, the sparse autoencoder, deep autoencoder, convolutional autoencoder. So this just makes you understand that there are different types. So the first three use cases here are based on convolutional autoencoders. And the last like three, which are image search, data compression, also we have topic modeling and information retrieval. In these particular cases, we can use only deep autoencoders. So we will see the difference, but as the name shows, I always believe in learning things based on their name, because names, most of the cases are significant. Now, there is kind of significant. Yes, significant. Okay, so convolutional autoencoders, the word convolutional, like convolutional neural networks, for example, convolutional autoencoders. So the word convolution mentioned that there is some kind of convolutional layers. However, deep autoencoders, there is no word convolution, so we don't talk about any convolutional layer. We only talk about many. Deep means we have too many, I would say, layers, and these are just like dense layers, but we have many, okay? So this is from where like I'm trying to quickly give you an overview about what we will see later. So, okay, this set of examples, I would say, is given, I chosen, honestly, to work on images, because in case of image, I feel like I see the difference and it's really interesting. But there is a more interesting probably use case is when we do not have image data. Last time we seen that we do not only deal with images, we can have kind of text data, and the storage is different. Remember, like what we said, we say if I have an image, it's kind of a matrix, a representation. And if I have a matrix, I can even move to the tensor representation if I have colored image in the RGB space. However, if I have a word, I can encode that into simple vector, for example. So now I will focus on the case of words, or if you have only, I would say, sentences, if you have natural language. So in the case of NLP, I would say natural language processing, we can use autoencoders as well for example, text cleaning. And here it's bothers everyone, at least it makes me crazy sometimes, is when especially you are quick and especially if you are fighting. So in the fighting mood, so you're writing something, it shows you something else. So these like auto corrections in iPhone mainly are used or based on autoencoders, I would say. Also, for sentiment analysis, we use autoencoders. So given, I would say, for example, tweets or Facebook posts or whatever, like input, which is in kind of text. So we try to make sense of that text, I would say. So if I have, for example, my experience, I would say so far has been fantastic. Kind of, there is kind of positivity in this sentence, so it could be classified as positive. We kind of analyze the like sentiments in here. For example, the protect is okay, I guess. It's kind of neutral, and your support, like team, is useless. So this is probably the case of anger or claim. So it's kind of negative. So here we can use autoencoders to do this. Okay, we can use them also in a more interesting probably use case, which is detecting text anomalies, especially if you like banking systems and so on. Text generation as well. You see ChatGPT and generating text itself, or sometimes you ask in your prompt, write in that style or answer in that style or correct in that style. So text generation is also mainly based on autoencoders. We can also use it for translation, let me say. And probably like for translations here, it can be like used to translate from one language to another by learning kind of compact representation of the sentences in different languages. And it's going to, what it's going to do is going to do the mapping between these different languages. So mainly this is how it works. So another interesting use case is text summarization, where autoencoders in NLP, for example, can act like writers, for example. And in this case, they can like condense kind of long documents in shorter or summarized versions, let's say. Okay, so it's mainly when you give to ChatGPT some very long text and you say make it shorter. So maybe it's using kind of autoencoders. So in this class, mainly I am going to focus on autoencoders in the particular case of images, because I am probably more a computer vision person who mainly, even in my research, in my PhD, in my like current projects, I do work with images more than text. But if you guys are interested in text, why not? So I can make like more videos in like probably seeing some of these use cases, or in general autoencoders in the case of NLP. Okay, we can do that, but I prefer images for now. Only reason maybe because we will see in LLMs and in later in this class a lot of text part. So I want to make it in between, like we are working at the same time on images, on text, and diverse input types. Okay, So just let me know if everything is okay, if you have any questions, if you need anything. So I am like kind of flexible and I can even adjust the content. I can add more content. So it depends on your motivation as well. Okay, so keep all that aside and let's understand these interesting autoencoders. What are they mean? So here we are going to, first of all, like I said, when we call something, give the name, it means a lot. Like if I am calling something autoencoder and one day someone is asking you what are autoencoders, just let your brain think autoencoder, thinking loud like voice. There is the word auto encoding. So it's mainly containing the word auto, which is automatically, and encoding, it's clear that we are encoding data. So auto encoding is like we are automatically encoding data. And the word auto itself, it shows that this happened, there is kind of self-encoding, okay? So this kind of even like the model or the autoencoders in this case is kind of like it teaches itself how to represent the input, okay? So instead of like having us manually designing the features, like in typical or traditional machine learning, in this case, the model learns these representation on its own. Okay, this is the magic. And that is why we call it autoencoders. Okay, so what are they again? They are like learning by themselves. Now, how they are learning by themselves? Mainly they are kind of neural networks. They're a particular class of neural networks, and they are designed to learn efficient representation of the data. This is how they encode the data. Then into that, latent representation is very important. And we are then going to like decode that and get our final output. So we are going to, what's happening mainly that we are trying to reconstruct the input, okay? And so this X hat, I had a problem by inserting the mathematical formulas into the slides. Later, I was trying to take some screenshots and did it. So just I will just fix it when I'm sharing with you the content. But mainly, autoencoders, they are having two blocks. The first block, to not say three, I will focus on two now. Okay, so the first block is the encoder. It compresses the input into a smaller representation. And this is the component which is latent space of the code. And then we have the decoder part, which reconstructs the original data from that compressed form. Okay, so as I mentioned, they are unsupervised models. So if one day I ask in the exam, I ask in general, I do not ask about the particular use case, like for generating high resolution or something to tell me that it's supervised. So I ask in general. So in general, autoencoders are unsupervised models, okay? And in this case, what we mean is that we don't need any labeled data. We have our input, we focus on that, and we are having the reconstructed version of that input, whether it is like a colored image, whether it is like a cleaner or like a more clear version. So it depends on the use case, but in all cases, we do not use supervised data. We use unsupervised data, which is just like kind of the input image, the trained data and test data, for sure, we'll see that, but it's unsupervised models, okay? Now, this is the architecture, so, all right. Mainly how it works. So let's start with the basic idea of autoencoders. So an autoencoder is a simple type, as I mentioned, of neural networks that learns to compress data into smaller representation. So this is the smaller representation that I talk about. So from this smaller representation, we are going to reconstruct this image again. So starting from now, you are going to see these numbers, or I would say digits. So these digits are, I previously explained. So this is MNIST dataset. These are samples, examples, I would say, from images that belong to a very famous dataset, which is called MNIST dataset. So MNIST dataset contains kind of 70K images, 60K of them usually used for training the model, 10K, sorry, they are using to test the model. And it contains numbers like from 0 to 9 digits. And for each digit, we are like having many representation. You know, the way you write number 1 is not the way I write number 1, like someone else writes number 1. So in this case, for each class from like 0 to 9, we having many representation how to write 0 many times, many examples. We call them samples. How to write number 2, we have many samples. And that are used for training neural networks, autoencoders, or no matter what the task that we are doing, okay? Now, so this is the X and X hat. I told you I was working hard on writing that. Okay, so the idea now is that the input that we have, okay, we are going to denote that as X. So this is our input. And the input mainly is in kind of high dimension, okay? So what we will do is that we are going to have the compressed representation of the input. In other words, we are going to move towards a lower dimensional encoding, okay? This is the mainly objective. So this is usually called Z, and it's kind of a compressed representation of the original image. The goal in this case is what? It's mainly to capture the most important features of the data while kind of removing redundancy, because sometimes there is kind of redundancy. Oh, this is black somehow. So I'm just giving an example. So what we do is that we keep the most important features. So, okay, and why you would ask why we do keep these important features? The answer is mainly is efficiency. So we want to have that to make this Z vector kind of efficient representation because it has a huge impact on the result, okay? Since like from this like representation, we are going to go through the decoder part. This decoder takes like this compressed version, and the result like it's going to kind of rebuild the original image, okay? So you see here, this is the original image. This is the reconstructed, sorry, or rebuilt like version. And there is a difference somehow, but at the end it's number 2 if it's mainly, this is the result, okay? So this reconstructed version we denote like, or the output or the result, we call X hat, okay? So don't feel afraid when you see X, X hat, and Z and all this. It's just like we are naming things. You see, as simple as this. Your input is the X. If we are trying to make it into like the latent representation, we are only capturing the important features, that is Z. And then like if we are reconstructing the output of the decoder, that is X hat. So why I'm saying this, it's mainly like because what we are doing mainly here is that we are designing, I would say, a neural network. And this neural network is not any neural network, it's like kind of autoencoder. So there is the idea of training the model, okay? There is, I was mentioning that we have trained data, we have test data, and so on. So how do we train our model in this case mainly, and how could we probably evaluate the X hat as compared to X? So the idea here is, as I previously explained it for neural networks, is we work on minimizing the difference between X and X hat. So we want that, it's our goal mainly, to have that reconstructed input is as like similar as possible to the original input. So how we do that mainly in neural network? Or so I was like explaining before, usually we use what we call the mean square error. The mean square error is kind of a function here which takes into consideration both the input image X, the output computed by this network or autoencoder, and we try to minimize the difference. So here you see the difference, and so we try to minimize this difference, okay? And so mainly this is, again, like I was mentioning, is unsupervised learning. There are no labels like involved. The model learns directly from the input itself. So here we are learning from the original image. Whenever we are reconstructing, we are comparing, we are minimizing the error or can increase. So we are learning from this metric, okay? So now there is probably kind of a discussion that could happen when it comes to the size of the encoder layer, or I would say the latent space Z. So this is very important. And what we want, what we wish, we have a big in the input, like huge, I would say, representation, the input itself. So we are compressing it. So if I will ask any of you, you probably will say, I say, which is the best Z that we can have? It's like you will say the smaller we have this Z is the best. So because the smaller Z is, like the more compression you get. But also don't forget or keep in mind that here, if you are making it as little as you can, it's making you lose more information, okay? So there is kind of contradiction here, conflicting objectives that we have. So there is kind of a trade-off between efficiency and the reconstruction quality. Because if you want to have probably better reconstruction results, maybe at some points you need to work like which is the best day that I may have, okay? So this is kind of a trade-off, and that's basically the heart of autoencoder, kind of a model, learns to encode and reconstruct its own input automatically, okay? So mainly there is nothing to add about autoencoders. These are what autoencoders, okay? Now, let's move to the interesting part, which is the different types of autoencoders. Okay, so coming to the most interesting part again. So we will start with a simple autoencoder, which is based on a fully connected layer. Mainly, we're going to use a single layer for the encoder, single layer for the decoder. Okay, so here is just a screenshot from the code. I'm going just to go through. Here you have the link, and I made it public. So if you're just going to click on this link, you're going to find the lab one, I was calling it. So we start with the first example and of one like autoencoder having a single fully connected layer. So going now to the notebook, you open it. It will open on Google Colab. I don't know if you guys are familiar with coding or not familiar with coding, but what I can tell you is that please don't be afraid when we talk about coding. Coding is the best part and it's the engineering side, and mainly you must do it. So don't feel afraid when you see a long like code or when you see a long, I would say, notebook. So you can just understand things step by step. This is what I can tell you. So in this notebook, mainly I've been like based on Keras documentation. I found like similar like code and explanation in the like building autoencoders in Keras. So I couldn't find a better example to teach you with because it's very nice pedagogical, you can see. So we are going to learn with this example, okay? So here I can keep you with some readings to read more what are autoencoders, to get more information. And here we are going to start building the simplest possible autoencoder, okay? So this is the code, and yep, it starts from here. So if you are not familiar with Google Colab, it's very easy to use. It's even better in some, especially for like learning purpose, than downloading things locally. It takes space, takes memory. Sometimes you have error, problems with Python versions, and so on. So here it's kind of environment ready, clear, like setup final for you. You can just use it and it's going to run in the cloud. Okay, so it's a service provided, I would say, by Google and mainly like very useful. So you're going to open, it's related to your Google account, okay? So you log in with your Google account and you can start creating notebooks, okay? So I will show you how you will create your first notebook probably in this class, but let's understand the code first, okay? So we were learning about autoencoder, and now we have the simple one. So autoencoders, we're going to learn building. use libraries. So we are going to use Keras, okay? And for this, we need to import that. So we need to have it so we can use it. We can use different layers that Keras provides, okay? So from Keras, we are going to use the different layers. So this is why we mentioned that from Keras, we are going to import layers, okay? And we start. So the first thing is like we are going to provide the size of our encoded representation. So encoded dim, so it's known like we call it encoded dim. This is the variable that we are going to have. And let's suppose that what we are going to have is dimension 32, okay? You can play later, I would say, with the code. You can edit this dimension. You can try to increase, you try to decrease, and you see the impact on your final output, okay? So this is what I'm talking about. So this representation, it has impact on your final output. So here we have many layers. The input layer in this example goes through 3 layers for encoding, 3 layers for decoding, okay? So this is a deep version. We will see only what if we have one single layer for the encoder, one single layer for the decoder. So this is why, and so we are discussing the dimension of the encoded representation. So in this case, we have our input image, and we are going to read that through like Keras. There is a layer called input, and we provide the shape of our input, okay? And then we'll go through the decoder. We mentioned that we have one fully connected layer, and fully connected layers, they are known or implemented. We call it 3D layer already in Keras. So it's called dense layer. Dense layer, it's a fully connected layer, okay? So for the encoded, we use only one dense layer. For the decoded also, we use one dense layer. So the first one, encoded, it applies this dense layer. I'll come back to the parameters. To what? To the encoded image, okay? So here, this layer, it applies like that to the original or the input like image or X, so it's input layer. Then for the decoder, so the decoded part, it has a dense layer, okay? And it's going like to decode what we have from the encoder's part, okay? So it takes here, it applies to the encoder. We call it sequential model. So the output from like the input, it goes to the encoder, the output from the encoder, it goes to the decoder, and so, okay? So here, like we have again, the input shape is 784, okay? It must be here the same as the output, okay? So the decoder is going to give you as output the image x hat, I would say, having the same dimension as the input x, okay? They are the same. So in terms of number, you have 784 here, you have 784 there, it's the same. So now what we use is kind of within the fully connected layer or the dense layer, we use the activation functions, okay? So the last layer has sigmoid activation function because we talk about probability values and so on. Otherwise, in the encoder part, we can simply use the ReLU activation function, okay? I previously explained activation function when I was teaching you neural networks, okay? So what this model is mainly doing is that it's mapping an input into, I would say, to its reconstruction. So the autoencoder, it's a model that have the input image, it's going mainly to map it to the reconstruction after having the decoder. So the decoder already is having or applied on the encoder, okay? We don't say where is the encoder is going. The encoder is already here, the dense layer from the decoder is already applied to the encoder. So this is just as simple as this, okay? So here it's like kind of a simple or a single fully connected neural layer, like to encode and decode, okay? So now let's create the separate model. So our model is like for encoder, we have input image we are calling encoder, and encoded, okay? We call models from Keras, okay? Now we are having our model. So our encoder, we have 32-dimensional input, okay? It's the dimension. And like we are going to retrieve what we call the last layer of the autoencoder model coming from the decoder, okay? So last layers, always we refer that to the index -1, okay? So here the last layer is -1, okay? So this is the decoder layer, and our decoder is mainly getting as input the encoded input, okay? And we apply the decoder layer to the encoded input, okay? So this is our model. Now we are defining the model using these like already defined layers, encoded and decoded. Now here we have our model. What happens then? Usually you create your model. How it happens? You always must have some kind of pattern. So the first element is that usually in a separate cell, you import whatever useful libraries that you will use. Next, you define your model, okay? After defining your model, you are going like to compile your model, okay? And usually, sometimes we put the pre-processing step, importing data before defining the model, but in this case, it's just coming here. So we are going to train the model, and for training, we need some data. So what data, as I was mentioning previously, we are going to use the MNIST digits, okay? So we're going to compile, and for compiling, we use kind of an optimizer. Here we are using ADA, and the binary cross-entropy loss. So what loss function we are going to use in our autoencoder, okay? So let's train the model, and to do that, we need the data. We can do this even before defining the model, but here we are importing the data. And so our data set here already exists in Keras, in data sets, so we are going to import MList. And we are going to do some pre-processing, so this is why we can use the library NumPy as well. We denote it as NP, okay? It's an abbreviation just we give, so later when we call NumPy, we call it NP instead of writing NumPy all the time. So our data, we are going to load some training data and test data from the MNIST dataset. So we apply the method .load data. Okay, our data is there. And by the way, so in Google Colab, you have some cells here, I would say, are used for text. So here you just add text to write something to kind of I explain for you. And some cells are there for writing the code. So these cells just here, you can like run them. You just click on this and it's going to run yourself, for example, okay? Here is, I'm going to import the data again. It's not a problem. But I'm not running the cells because the training later will take some time. I don't want to make my videos more long. I know probably you first thing check the length of the video, but believe me, I do my best to maintain the quality as well. So we need to explain things, to take our time to explain things. Okay, anyways, so now we have our X train, we have our X test, we have our like training data and test data. We have like them in the type here. We want to use this like as vectors or reshape them from the original size, which is mainly 28 by 28. We want to flatten them to have them the size like a vector, like 784. This is from where the 784 is coming. It's by multiplying the width and the length, the image of each of the inputs. So this one, for example, it has like here, you have like the size of this image, it's mainly you have here 28 pixel, okay? And here you have 28 pixel, okay? So the idea is that by multiplying 28 by 28, you are going to, instead of having them represented as a matrix, 2D matrix in this case, this is dimension 1, dimension 2, you are going to have them flattened. So you have value for first pixel, second pixel, third pixel. You are going to have all these from the first, I would say, row, the next one, the next one. You're going to store them as pixels, okay? So this is how you are moving to the 1D in this case. And so the length is going to be 28 by 28, which is 784, okay? Let's let me do this. Okay. So now let's just move on quickly. We have our training data. What we need to do is that to reshape that. So we have 6,000 training image with a dimension 784, 10K images with a dimension 784. So in this case, we don't have only the number of two. We have all the training set, 60,000. And for this test, we have 10,000, okay? So this is just, we are uploading the dataset as it is. So mnet, it's like this, okay? Next, now we are going to fit our model, to train our model, given this data we give xtrain and xtrain, okay? And we are going to train it for 50 epochs with a batch size 256. And shuffle through means we are going to not keep things in order. We are going just like when you're playing cards, you change the order, okay? So we don't keep all the first samples number 2, then number 3, then number 4. We remove this order. Because sometimes when you are training neural networks and you don't know to shuffle your data, it happens that probably if we have, in this case, digits from 0 to 9. For first 6K, I would say it will be from, let's say, 0 to 7. Then the last 10K will be from 8 and 9, let's say. So if I'm training on 0, 1, 2, 3, 4, 5, 6, 7, and testing on 8, 9, it's testing on data we didn't see. So in this case, it absolutely makes problem. So we always shuffle the data. So we have sometimes first 2, then 3, then 5, then 3, then 2, then like in an ordered way, okay? And validation data is X test, and sorry, it's going to be X test, okay? Okay, so it takes some time. I'm not going to waste the time, but after 50 epochs, what we have is a loss value which is equal to 0.09, okay? So what happens is that the loss, it keeps decreasing, okay? So it starts somehow and start decreasing, okay? And reaching this value, okay? So what we will do now is that we are going to check if we give a new image, okay? What will happen? Is it going to be, I would say, compressed in a nice way? It's not going to be compressed in a nice way. So this is just a plot to visualize things. This is, in the first row, we find our data from the MD dataset as it is, okay? So this is our initial data. As output from the autoencoder, we have this representation. Mainly they are not bad, okay? So you see that there is a loss of quality, okay? But it's the same input. So this is the idea of autoencoders, and this is one of the use cases. So probably we don't have that perfect, I would say, output. The reason can be that due to the architecture, to the hyperparameters, too many things. So as an exercise, probably I will ask you to do is you are going to create a neural network, okay, that mainly can kind of enhance these results, okay? So in this case, you are going to just add a sparsity constraint to the encoded representation, okay? And here I will probably open the parentheses about the similarity between neural networks, okay, and autoencoders in particular, and the famous PCA, Principal Component Analysis. Okay, here you have the link. You can read more about Principal Component Analysis. That's just in Wikipedia. But the idea is, so if you don't know PCA, it's not a problem. I will just give you the result, the outputs in very quickly, I would say. So autoencoders are like neural networks version of PCA. Keep in mind. So the only difference is that autoencoders are smarter. Smarter in terms that PCA only computes linear relationships. It's kind of straight line patterns. And the autoencoder, they can learn nonlinear and more complex patterns like curves, like texture, like shapes, and so on. And this we see in the use case, like different use cases that we covered so far. So when your autoencoder's hidden layer is small, like the example we seen, like only we have one hidden layer, it here ends up like doing something which is very similar to PCA, which is kind of compressing, the data into fewer dimensions to keep only the most useful information. So here we can say that as this model only contains a single, I would say, layer. Okay, this is the simplest possible autoencoder. We only have one dense layer for the encoder, one in the decoder. So mainly this works like PCA. Still, PCA probably is not clear in your mind. I know that, so don't worry. I'm coming back to explain PCA, okay? Then I will come to this exercise now. Let's go through PCA. So PCA, again, I give you this example of the shadow in the wall. And what I have here, it's the hand, okay? And if I switch off the light, I put some source of light, you will see like in the slides here. So the projection or the shadow of my hand is going to show. Now, from this projection, we can say that this is a hand. It's clear that this is a hand. Now let's consider not moving the hand because our input is always the same. No, we're not doing like this. This is kind of deformation or attack or things that are happening. We will not do that. I will keep my hand straight like this, and the projection will show you just the projection of the hand. You will see the fingers clearly and so on. So at this given moment T, okay? But this, without changing the hand shape, I'm not moving anything, you can just change the direction. So it can show something like this. So the projection from this point, of my hand, if the light is here, it will show you some line like this. So this, if I show to anyone, probably will not guess that this is a hand, okay? Like the example of a dino and that like latent like variables we see, but keep it aside. Now we have the hand. The hand at some point, if I choose this axis to show you, can maybe you only see the shadow for sure. You cannot predict or guess that this is a hand. This probably can take us to a very important thing, like there is an axis from which if I see this thing, it shows me clearly that thing. We call them principal components, okay? So here, how it works. So I will move to very more clear example. Now, this is my hand. It's the data in the 3D space, okay? And the projection is the data in the 2D space. So the projection in the 2D space depends on the position probably of my hands at that time. Even that I'm not moving my hands, I'm not doing any complex like transformation. Now, in like more simple example, if you are going to imagine that here you have your data, and this data has many features. Like for example, an image, I would say you have thousands of pixels, okay? PCA, how it works? It looks for a smaller set of new features, okay, that captures kind of these new features, they capture most of the important information, okay? So like in the hand, I am only capturing the projection. I have the important information that this is a hand, okay? Without having all the details of my hand, all the information, all the like from all the perspectives or viewpoints, I would say. So only like from a given like setting, we have the smaller or set of features containing the whole information. At the end, this is a hand, okay? So how to select that? So the idea is that instead of having here 1,000 numbers, I would say image, I mean image with 1,000 numbers, maybe I can describe that image just with 20 numbers. Okay, it's just an example, okay, abstraction. And so still I will understand that this is that image. The same with the hand. I just, with that projection, given this position, I understand that this is a hand. So PCA is mainly a mathematical way to find the directions that explain most of the variation in your data. I would say the pattern that matters the most, okay? So this is PCA notes, but PCA, when it comes to mathematics, it took me personally maybe one semester to learn PCA, okay? And I believe there must be probably a class 14 weeks class for learning PCA, okay? Because we need to understand each step. Each step, there is a lot of math behind. We need to understand that algebra and that like equations and so on. So it takes lots of time. But this is mainly what is PCA in simple words. Now we visualize things. And so we try again to simplify things. So let's imagine here what we have. Data set with only 2 columns, okay? Because the examples that I'm giving so far, like the hand main is 3D space, we are moving to D space. Here again, we have the 3D space. PCA is applied to move on the 1D space. Okay, so here, 2D, sorry. Here we will move from 2D to 1D, okay? So we are imagining that we have the data set with only like 2 columns. So here you have your x's and here you have your y's, okay? And the idea is that using these 2 columns, I want to find a new column, which is the one here, which is moving, because there is infinity of possible columns, okay? But what we are looking for is that one, a new column that better, I would say, represent your data, okay? So this is probably going kind of summarize the 2 columns into 1 column, okay? So this new column can be kind of through of as a line, like here. It can probably passes through the points, all the data points, and such a line can be represented as a linear combination of 2 columns and explains the maximum variation present in these 2 columns, okay? So this is the main target. In what direction do you think probably this line kind of should stop so that it covers the maximum variation of that point? So we can probably stop it right here. So for me, such a line like should be in this direction, in the direction that minimizes. So in red here we plot the loss, which is if we have big difference or we are more far or more near. So we need to be more near from all points, maximum points, I would say. So this line on the right here, it like minimizes the perpendicular distance. So this is the perpendicular distance of each point from the line. Okay, so these line like plots show you the distance, and here we have it even many points are just very, very near to that line. Okay, so each point we measure that perpendicular distance, and probably something like this could be seen as a principal component. Okay, so this is how PCA works. Why I'm telling you this? Because don't forget that we just learning about autoencoders. Don't sleep. We are in a PCA context because I mentioned that at a given setting, when we have the simplest autoencoder, it can work as a as principal component analysis or PCA. And now we took a look on this PCA, how it works mainly. We will come back to the smarter version of our PCA, which is our autoencoders. Why I'm saying they are a smarter version of PCA? Because if we are going to compare, PCA usually gives you something like this, which is kind of linear. However, for autoencoders, we can have the nonlinear, because we have that activation functions. They introduce nonlinearity to neural networks. So we learned all that. This is how or from where it's coming that autoencoders, they provide nonlinear transformation. It's due to the nonlinear activation functions, and probably in deep autoencoders, we will see later, we can have multiple layers as well. Also, in the case of convolutional autoencoders that we will also cover today, an autoencoder doesn't have to learn dense layers. There is also the feature extraction or like block, which are the convolutional layers, and these also contribute to the autoencoder learning, okay? And they are also higher in terms of efficiency, so more efficient to learn several layers with an autoencoder. It is more efficient, okay? In addition, so we have multiple transformation, which gives like a representation as the output of each layer, okay? So this is how we are understanding how we are moving from PCA to like linear, basic, and so on, to autoencoders with the different architectures, okay? Now, the simple autoencoder I was just teaching, has only one single layer, and it like kind of very like simple. Now, what we do is that we introduce what we call sparse autoencoder. So they pretty look similar to the previous model. So in the previous model, we only have one fully connected layer for the encoder, one fully connected layer in the decoder. So one dense encoder, one dense for the decoder. However, the difference here, like it's significant kind of difference, which is adding the sparsity of the encoder representation. So our new model in this case yields encoded representation, okay? So that are, if you compare these results to the results we obtained from previous model, now they are, you see these results, now the output when you have only the dense layer, compare them to the output if you have that dense layer with kind of activity regularizer. So they are twice sparser, okay? So we understood that this is sparse autoencoder. It's very important. We constructed in terms of coding by adding this parameter, activity regularizers. So we give the regularizers L1 distance, and we give it here, it's a number parameter, okay? 10 exponential minus 5. This is just a hyperparameter. You can just make modification. You try minus 4, minus 6, minus 7. And now this is going to be your task mainly, is that you are going to return the notebook having the the sparsity constraint to the encoded representation. So here I have just an example. So what you will do is that you will take the cells, you're going to create your own like notebook, okay? You create new notebook in your drive. This notebook is empty. So what you have to do is, you can explain for sure with text, if you want something to tell me something. You try to take, it's okay, encourage copy paste, because in coding, we all know that no one is just writing everything by himself. So we try to take the pattern, like I'm saying, the import, like the layers, where it tells that they define your data MNIST, it's divided to train and test, and only this part of the code which defines your sparsity constraint added to the encoder side, okay? So this is what I need. You are going then to train it for 100 epochs. I'm not showing here the training details, but you can check here. Here is an example of how to train the model, okay? So you can just mainly copy paste, but I want you to learn. Doing things yourself always give you more confidence. So here your autoencoder dot fit. You're giving trying to train for 50 epochs, for 100 epochs. Just show me your creativity and your final results. You try to edit. You can have many copies and you can just come up with a conclusion, what you did, what probably given you the best results in terms of changing this parameter here, hyperparameter, and so on. So, okay, at the end, you'll have a plot like this for each case, showing you, like, for example, after 100 epoch, you will have the loss value X depends, and this, like, results is, for your case, it's going to be how. You can just even implement them as they are, okay? You cannot even play with the hyperparameters. It's up to you, okay? So, but the minimum thing I want you to run, like to have one notebook in which you are like adding sparsity constraint into a autoencoder or the encoded representation and training it and plotting the final output by yourself. You just use this and copy paste some cells, will work. Now we move on from having one single cell, no matter that it contains sparse information or it does not, we will move to deep autoencoders. Deep autoencoders mainly, in the previous version, we have a single layer for the encoded and a single layer for the decoded. Now we will, deep learning, it's when we have more layers. Okay, so here we will have 3 layers for the encoded part, 3 layers for the decoded part. Exactly like this architecture. So here I have 3 layers and here I have 3 layers, okay? And if you see, there is kind of what do we call that? It's symmetric, okay? So this size is same as this size is same as this size is same as this size, and the input size is same as the output size, okay? Note this. Because what we have here, in terms of length or number of neurons per fully connected layer, the first layer, which is so the input layer is having the size 28 multiplied by 28, which is 784. So from that, we will move to lower dimension. We will have for the first layer 128 dimension. Then we'll reduce that 128. We will have, I would love to just draw things here, so you will understand me maybe. So the first layer, so the input dimension here, it's 700, 84. Okay. Perfect. Now we are going for the first layer of the encoded to have 128. Then this size is going to be less, to decrease. So we will have 64. Okay. Next, now we have 32. It's much more or less. Okay. So it's kind of moving from dimension here 784 to 32. Okay, there is a drop here. We have to see. Next, now it's going to be kind of symmetric. So this 32, we will have it here. Okay, so here is it. 32 is the least. Okay, so it's the Z. Fine. Now it's symmetric. So we will have 64. Okay, so again, now we will have 128. It's here. See? So 128. Yup. Then we will reconstruct the input. So we have the X hat. This is our X. And this is X hat, which is the output layer. Okay. So which is having the dimension same as the input. Okay. Your input here is equal to the output. This 128 is same like this 128. This 64 is same as this 64, and here you have your 32. Okay. Now what we will do is the following. We have our code, it's clear. We have many layers. This is the encoder, this is the decoder, and so it's clear. We are going, or I already have the version of this model being trained, being like, I would say compiled first, compiled, then trained, then we have the final results that we are going probably to compare to what we had before. So in this case, we're just increasing the number of epochs to 100. After that, we end up having a loss which is equal 0.8. If you remember in the previous version, which is the fully connected, we only have 0.9. So now we have 0.8. Remember that 0.8 is better than 0.9 in terms of loss, because always the more it's near to 1 means it's like 100. So you have more error. So we want to be always more near to the 0. So 0.8 is better than 0.9 in terms of error. Okay, so this is a bit better than our previous model. Now visualizing this like amelioration could be seen here if you can compare it to the previous version and so on. Next, or last part, probably we have the convolutional autoencoder for image sampling. So convolutional autoencoders is just kind of having or using the convolutional layer, and usually after convolutional layer we have the max pooling operation happening within the encoder part. So max pooling, just to remind you, if I have an image, I apply max pooling, is kind of reducing the dimension. And this is how we are reducing the dimension. So for example, if I have max pooling window 2 by 2, it means I consider the matrix of, or this 2 by 2 like window, which are these 4 pixels I'm going to compare, and I will retain the max. So here the max is 34, the max here is 54, the max here is 52, and the max here is 56. So these are known as activation maps, the maximum values for each window. Now we need also probably some like architectures to maintain the indices for these pooling indices for these values. So like, for example, like here we have the index of 34 is 3, okay? So the index for 50 like 1, it's 1. So 0, 1, 2, 3, 0, 1, 2, 3 is like this. So 41 here it's 56, so it's at the index 0. So this is where we have 0. So 0 here 1, so 652 is the like position, let's say place, and its first position and so on. Okay. Next, now this is for max pooling. For the decoder part, we use upsampling. So we use for sure the convolutional layer, but we want to reconstruct. So the output in this case for max pooling, the output is follow the direction of the arrow, so less dimension. Okay. So here from this less like dimension, we will go to upsampling, bigger dimension. So from dimension 2 by 2, I will move on to dimension, what we say, 4 by 4. How I will do that? So I will just put the max values in their position. So the 34 in the position 3, the 54 in the position 1, the 52 in the position 1, the 56 here in the position 0. So now and then the rest for each case I will put zeros, okay? So here I have the same size. I just get rid, I would say, of the useless information. I maintain the important features. And this is why sometimes you find it's kind of fuzzy and so on. Okay, so here we have 3 convolutional layers with like 3 max pooling layers for the encoder, 3 convolutional layers with 3 upsampling 2D convolutional, upsampling 2D layers. So these are upsampling layers. And at the end, so this is mainly our model. It has this as a result. So you see this fuzzy mainly because here we have zeros somehow, okay? This explains the result, okay? And don't forget that the application of convolutional autoencoders could be for image reconstruction, image colorization as well, or even generating higher resolution images like we've seen so far. Another interesting application could be for image denoising. So autoencoders could be kind of image denoising models. I kept like here in the notebook also an example of image. Okay, this is the convolutional model. It's mainly the same. We define it, we bring our data, train and test, we reshape. And by the way, here probably I want to comment on the shape. The MNIST dataset, it's by default has it's a gray level or black and white at some points data set. But here you have the number 3 because it could be adapted to the famous like architecture or like ImageNet or that work on convolutional architectures that work on 3 channels, the RGB. So sometimes we have this representation, but in our case, we just did some kind of we are using it as it exists, okay? So we are using the original MNIST, which has already this shape. So what we do is that we just get rid out of these 3. So we are just kind of reshaping. So we have only only one channel, and we have the shape 28 by 28 one, which allow us to feed it to the convolutional neural network. We train our model again for 50 epochs and so on. And we can have the ready visualization here. I'm just showing you from the website. I told you here it has the like code and all. So in this case, it's just running it locally. If you will do that, you can use TensorBoard. Otherwise, we can just go through this visualization. We see how the loss and the validation loss, they are decreasing, okay? And we again compare the results and we see the impact of convolutional layer. So here now the interesting application where we have the denoising. Now we bring our MNIST data set. What we will do is that we're going to add some noise somehow, noise factor 0.5. And so this will generate the images, noisy images as you see them here. And next we are going to use like this architecture, which is conv, max pooling layers, conv 2D layers with upsampling layers. This is just an example of a model. We train it and we fit it and we kind of try to have the final result or output. So in this case, probably it's also possible to visualize what actually happened within the 128 dimensional encoded representation. We can visualize the output and so on. This is a very interesting application for denoising, okay? Now the last thing is autoencoders for language tasks, I would say. Or in this case, rather than using the 2D images, probably we can, this is an introduction to move probably to NLP things, but we can even use vectors, okay? This is the starting point. So if we use vectors, the only thing is that we can have this kind of parameters in the start where we define our time steps with length of your sequences. And then you are going to use, like, for example, the shapes depends on your time steps. You have your LSTM as a model to be used because it depends. Conv models or that's we are only using them for image data. If we have different representation like vectors, we can use different architectures or layers. So we use LSTM layers in this case, okay? So mainly that's it for today. And if you want to dive more into like autoencoders for NLP tasks, just let me know. Otherwise, I think that for image is more than enough. And I think if you have any questions, just never hesitate to send me messages, emails. You can just message in the Discord channel. And thank you so much. Okay. Thank you for watching.